Hi everyone, I'm Lily Long and welcome to Physics 2's Lab 3. In this lab, we focus on the distance dependence between a solid bar magnet and a magnet sensor versus the distance dependence that can be calculated using derivations of the Biot-Savart law. We mainly use one cylindrical bar magnet, the Physics Toolbox magnetometer app, or some similar to it, 2-meter sticks, and a provided Excel sheet for data collection. At the end, we could conclude that for our on-axis calculations, n was negative 3.0691, and for our off-axis calculations, our magnetic field due to the bar magnet was negative 8.09 times 10 to the negative 6, negative 4.52 times 10 to the negative 5th, and negative 3.22 times 10 to the negative 5th. Teslas, which could be compared to our magnetic field of the bar magnet based off the Biot-Savart model, which ended up being 4.36 times 10 to the negative 6, 1.39 times 10 to the negative 5th, and 0. The vast differences, especially in the Z component, can be explained by the interferences around our experimental area that impose their own magnetic fields that were then picked up by our sensors. The main principle we used during this lab was the Biot-Savart law, which measures the electromagnetic field between a current and observation point. The on-axis derivation B equals mu naught over 4 pi times 2 mu divided by r cubed, where r is the distance between the sensor and the magnet, is mainly used for dipoles when r is much greater than s. The off-axis derivation used is actually the general form of the formula, which is B equals mu naught over 4 pi times 1 over r cubed times 3 times the dot product of mu and r hat times r hat minus mu. Later on, we will use this mu in its unit vector form. Some observations we observed when measuring the magnetic field were that the further away the bar magnet was away from the sensor, the closer the magnetic field was to 0, and as the sensor was closer to the magnet, the x component specifically increased when we initially located our sensor, where the magnetic field due to the Earth could be orthogonal and thus would not affect the x component as much. In order to obtain mu, we first applied the natural log of our Bx values versus the natural log of the distances between the magnet and sensor that would allow for the magnitudes to be 20, 70, 120, and 220 microteslas. We then were provided a line of best fit where m was our value and n in the distance dependency formula, which is the magnitude of B of the bar magnet, is equal to kr to the nth power, and B was the natural log of k. By setting the approximation formula to the on-axis dipole formula for magnetic fields, we were able to cancel out r to the third and solve for mu after solving for k, which was 4.99 times 10 to the negative 7th. Mu was equal to 2.499 amps times meters squared. In our code, we used mu to create vectors based off the magnet's unit vector at the origin. The general Biot-Savart law was used in the dipole B function, which allowed for a magnetic field to be calculated for each arrow in the field if used. When creating arrows, a scale of 350 was used for visibility and was applied to every arrow in our code. The distance between the arrows and the origin ended up being 0.15 meters, also based on visibility limits in our code. The first 2 arrows in the orange were created to represent the on-axis magnetic fields, and the next 4 cyan represent the perpendicular alignment of the field for the bar magnet. The last arrow created in magenta represented the magnetic field 45 degrees off-axis based on the location of the bar magnet. The true distance was the hypotenuse of the 2 perpendicular distances which stretched from the magnet to the intersection of the 2 tapes, which indicates the exact location of the sensor. This distance came out to be 0.299813 meters. Finally, we were able to run our code and witness the magnetic field of the bar magnet, as well as compare the off-axis magnetic field we measured, as noted in the Excel cells, to the off-axis field magnetic field derived from the Biot-Savart's general model equation that was calculated in GlowScript. When obtaining the y component of our measured magnetic field, we had to subtract the Earth's magnetic field's y component from our measured y component, as the Earth's field was acting on the sensor at this location. However, there is still much interference from other objects, such as metal objects or electronics near our experimental area, as the 2 magnetic field vectors are quite different, especially on the z-axis. Some things to consider afterwards are 1. If we hadn't oriented the experiment to compensate for magnetic north and instead laid the experiment at an intermediate angle, then the resultant vectors of the on-axis and off-axis magnetic fields would be larger because of the presence of the Earth's magnetic field. The distance dependency would be much less accurate because of this. And 2, if we were to stick 2 identical magnets together and run the experiment again, we would not see a difference in the direction of our magnetic fields, but the magnitudes of them would be much larger because of the simply strength of the magnetic field. Thank you and see you next lab.